Hello and welcome to the 8th part on Year 13 Differentiation for Edexcel's A-Level Maths course. So we've done quite a bit so far on the topic of differentiation, not just in Year 12 but this chapter here. And what we're going to do in this session is talk about differentiation implicitly, implicit differentiation. This is very useful if you're trying to differentiate or to find dy by dx over a function which is a mixture of x and y terms. So you have a mixture of functions of x and y together, and you can't isolate it in terms of just a function of x alone, then differentiating implicitly is a very powerful method to use. So before we do that, we do have 4 warm-up questions for you to attempt, so I'm going to show you them here. So my suggestion would be to press pause now, try these on your own, and then when you're ready to see the solutions, press play, then I'll guide you through how to do them, and hopefully your answers will agree with mine, and if not, hopefully we can learn some things along the way. Okay, so assuming you've paused the video here and are ready to see the solutions, let's have a look together at the solution to warm up question 1. So warm up question 1, we've got an arithmetic sequence which has first term a and common difference d. So there are formulas given in the formula book for the sum of the first n terms of an arithmetic sequence and geometric as well. So I'm going to just remind you of these first of all before we continue. So we're told about the first term a and common difference d. So the first thing to recall is that the nth term of an arithmetic sequence in A-level terminology is this. So the nth term, t subscript n, is a plus n minus 1 lots of the common difference. So you're not actually given that, so you do need to know this. The next ones you are given, but I'm going to show you where they come from, so they make more sense. So using this as the nth term, the sum of the first n terms is actually half the number of terms you add in together multiplied by the first one plus the last one. So the last term though, if you've got n you're adding together, the last term is the nth term, and so L is this thing here. So if I substitute L for the nth term, because L is the nth term, and then put in this expression for the nth term, so replace the nth term with a plus n minus 1 lots of d here, then we can neaten up this big bracket. So we're going to have a plus a, we can have 2a plus n minus 1 lots of d. So therefore the sum of the first n terms, s subscript n, we can either use this formula here or this one below. So as I say, I'm going to highlight these in purple. These two are equivalent. You're given these in the formula book. I just want to spend a minute trying to show you why these make sense. So we can now use this. So what we're told here is that the sum of the first 36 terms of this particular sequence, that's actually equal to the square of the sum of the first 6 terms. So we can now use this. So the sum of the first 36, we can say that's where n is 36. So in other words, we're going to have 36 over 2 2a plus n minus 1 lots of d. So for 36 terms, n is 36, so n minus 1 must be 35. So then n minus 1 times d must be 35d. So I've got plus 35 lots of d. So that's the sum of the first 36 terms. And we're told that's going to be equal to the square of the first 6. So when we've got 6 terms, n is n6. So if I choose n to be 6, same as 6 over 2. 2 lots of a. Then if n is 6, n minus 1 is 5. So we've got plus 5 lots of d. However, the whole lot of this is now going to be squared. So that whole thing is going to be squared as per what the question tells us. So our next job is now to neaten this up and then end up hopefully with this here. So 36 over 2 is obviously 18. So 18 times 2a, that gives 36a. 18 times 35, use your calculator if you want to, and definitely suggest it in fact, that gives 630. So 36a plus 630d Now here, we're going to have 6 over 2, which is 3, square that, which is 9. And then if I square out this bracket here, so 2a squared, all squared gives 4a squared. Multiply these two together and then double. So 2a times 5d is 10ad. We double that to 20ad. And 5d squared is 25d squared. So how we got this is we've squared everything. So 3 squared is 9. This whole bracket squared is this. You can now hopefully notice that both sides can be divided by 9. Obviously this one on the right hand side has a 9 factored out, so that's obvious. But looking here, the digit sum of 3, 6 and 6, 3, 0 are 9. So what we can do here as our final step is to divide both sides of this by 9. And when we do that, hopefully, you'll see we've got exactly what we needed. So then 36a divided by 9 is 4a, 70d, 9 divided by 9 cancels. So we have 4a plus 70d equals 4a squared plus 20ad plus 25d squared, exactly like we wanted to prove to begin with. So we've nailed question 1. Question 2. We've got a diagram below showing a sector OAB, and C is a midpoint of OB, and this angle theta is measured in radians. So given that the area of OAC is a quarter of the area of the whole sector, show that theta equals 2 sine theta. So again, we need to recall a few bits and pieces. So 2 theorems, or 2 equations you need to know rather. One is the area of any triangle, you told us from GCSE, and the second is how to calculate in terms of theta and in radians the angle of a sector, so the area of a sector. So these are the 2 equations you need to remember. So now we remember these equations, let's label in what we need. So the area of a triangle, AOC, is half times one side times the other. So I'll call this side A, that one B, and then sine C, that's just going to be theta essentially. And so just take what it says here. The triangle AOC is a quarter of the area of the sector. So I just do triangle equals quarter sector. So the triangle is half AB sine C. Now A, if you look here, goes from O to A. And so A is actually the same as R. So I'm just going to make a note there that A equals the same as the radius in this case. So it's a half times radius times B. Now it says here that B, well, from O to C, it actually says C is a midpoint. And so if O to B, again, is a radius, from O to C, it's going to be half of a radius. And so B, that's going to be half a radius. So we're going to multiply it by half of a radius. And then sine C is obviously just going to be sine theta. And we're told that equals a quarter of the area of the sector. So the area of the sector is going to be a half r squared theta. So it's a quarter half r squared theta. So that's what we have to begin with. So now what we can do is actually do quite a lot of cancellation and simplifying. So we see here we've got a half and an r squared. In fact, so what we can do here, we can cancel off that half with that half. We can divide through by r once and then again. Divide through by r twice, 1, 2. That'll cancel off the r squared here. So what we have on this side, we've got a half sine theta. And over on the right hand side, just have a quarter times theta. Then if we take this and just multiply through by 4 on both sides, we can therefore see a quarter theta times 4 is just going to be theta. And a half sine theta times 4 gives 2 sine thetas. So therefore, we've shown that theta equals 2 sine theta, which is what the question wanted us to do in the beginning. So we've nailed question 2. Let's have a look at the next one, question 3. Question 3, we're going back to some forces and statics. So we've got a uniform plank of mass 100 kilograms. So let's just add in information to this diagram step by step. So the first thing we're told is it's a uniform plank and it's got a length of 10 meters. Now if a plank is uniform, that means its center of mass can be considered acting from the middle of the object. So if it's 10 meters, that means its center of mass can be considered to act halfway along its length. So we can think of a center of mass as acting 5 meters along, acting down here. So we can have this in straight away. Whatever the weight is, it's going to be acting 5 meters away from A and also 5 meters away from this end as well. So it's going to be acting halfway along here. But what is the mass? Well, we're told the mass is 100 kilograms. Therefore, the weight, the force due to gravity acting at the middle, will be 100 G. So we can add in this is 100 G. I'm also told that this plank rests horizontally on 2 smooth supports, A and B. So that's A and that's B. So if this plank is resting on these supports will provide an upwards force to counteract its own weight. In other words, there will be 2 reactions, a reaction at A and a reaction at B. So we can take this 2 bits of information here about A and B and add on 2 forces, a reaction at A and a reaction at B. We don't know what these are yet, but label them on so they're ready to find, so we're not going to forget to find them when we need to. Next it mentions about this man, a mass of 80 kilograms. So he starts walking from one end of the plank A and goes along to the other end, and eventually he walks past B and it starts to tip over. So starting from A, it's going to walk along, stop, and then get nervous. Here he comes and he stops. We're told he's 80 kilograms, so his weight's going to be 80 G. And finally, to complete our diagram, we need to find the distance he can walk past B before the plank starts to tip. So we need to find this distance from B to the line of action of his weight from there to there. We don't know what this is. We're trying to find that. Let's call this distance X. Now, if a plank is going to tip, what that means is it's going to begin to balance about B. So it's going to pivot at B. This bit here is going to start to lift up where the man is. That's going to start to tilt downwards. So the key insight is when something's about to tip, one of the reactions will disappear. This reaction at A will disappear. So as the plank begins to tip, reaction at A will shrink because the plank will go up there and tip down there. So we can think of reaction as A as disappearing in this limiting case of tipping. So now we've got all the ingredients on our carefully labelled force diagram to actually work out what X is. So what I'm going to suggest we do is we take moments about B. So if we take moments about B, that therefore means we can forget the reaction at B because there's going to be no turning force due to reaction at B going through B. So moments about B. So clockwise. So turning clockwise about B is going to be the man's weight. So that's going to be force, which is 80 G, multiplied by the distance of the line of action from the force to the pivot, which is going to be this X. So 80 G times X. And that's the only clockwise force. So that'll equal the sum of all the anti-clockwise moments. So the anti-clockwise moments, there's no reaction there. The only thing we're going to have is the weight of the plank itself. And so the weight of the plank is 100 G. And the distance of the weight from B, if that's 7 and that's 5, this must be 2. So it's going to be 100 G times 2. So neatening it up, 80 GX equals 200 G. G's cancel on both sides. We can therefore work out this distance X. So therefore distance X is just going to be 200 divided by 80. If we do that, we're going to get that it's 2.5 meters. So he can walk 2.5 meters past B until he gets nervous and goes, whoa, I'm going to tip, I'm going to fall, I'm going to hurt myself, I'm going to walk back, if he's sensible. Finally, warm-up question 4. We have a box of mass 3 kilograms. It lies on a smooth horizontal floor, so we can completely forget friction. Friction is not a concern we need to worry about. A force of 3 newtons is angled downwards at 60 degrees to horizontal, causing the box to accelerate horizontally along the floor. Find the acceleration of the box. We know the mass of the box. We want to work out its acceleration. We know a force acting on the box. We can therefore apply F equals ma. We can apply Newton's second law to this. But first of all, because the box is going to be accelerating horizontally, we only need to concern ourselves with forces acting in a horizontal direction. This 3 newtons is acting diagonally. What we need to do is resolve this force into horizontal and vertical components. So this 3 Newton force, let's have it here. If I imagine a line going downwards and horizontally, like so, making a 60-degree angle, then we can use simple trig. And to be honest, at year 13, you need to know how to do this with a click of a finger, really. The opposite component to the angle is always going to be hypotenuse sine angle. So that's going to be 3 sine theta. This one here is going to be hypotenuse cos of the angle. In other words, the horizontal component will be 3 cosine 60. And so because we're only concerning ourselves with the horizontal components, all we need to do is think about the 3 cosine 60 component. So we're just looking at the 3 cos 60. So ultimately the question is to find the acceleration of the box. So let's now apply Newton's second law, F equals ma horizontally. So the horizontal force is 3 cosine 60. Mass is 3. Acceleration is what we're trying to find. So if we substitute in what we know, 3 cosine 60 equals 3 multiplied by a. Now cosine of 60, where 60 is in degrees, that's actually an exact trig value. That's going to be 0.5. So 3 times 0.5 is 1.5. So 1.5 equals 3 multiplied by a. Therefore a is 1.5 divided by 3, which is 0.5. Therefore the acceleration of this box along the floor horizontally is 0.5 meters per second to the minus 2. Now we've got the warm-up out of the way, let's have a look at this new strategy, implicit differentiation. Let's take a look. Implicit differentiation. So what is it and how do we do it? Well, so far you've seen various methods to differentiate equations of the form y equals f of x and x equals f of y. Some equations are difficult to rearrange into this form, but what we can usually do is differentiate these equations implicitly without needing to rearrange them. So implicit differentiation is when you've got a mixture of functions of x and typically functions of y, and they're either hard or impossible to rearrange. It's a method for differentiating it as a whole block without having to get messed up with having to rearrange something which is fairly awkward. So it's very useful, very powerful, and can actually help us to differentiate quite hard, horrible looking functions in a much simpler way than what you would have imagined possible. So how to do it? So first of all, how would you differentiate a function of y with respect to x? Obviously a function of x with respect to x is dead easy. For example, if f of x is x squared, differentiate that with respect to x would be 2x. I'm going to return to that example in a second. So first of all, let's use a chain rule to differentiate a function of y. Call it f of y, where f of y is something to do with y. I want to differentiate this in terms of y, but with respect to x. So first of all, I'm going to make a substitution. Let the function of y be called u. So then by the chain rule, we have this. So to differentiate the function of y, which I've put in brackets here, so the function of y with respect to x, where f of y is u, then du by dx is du by dy times dy by dx. So it looks like the dy's cancel, so you just have du by dx. That's not how calculus works, but it's just a quick double check to see if it does make sense just looking at it. So we differentiate the function of y with respect to y. So if you differentiate a function of y with respect to y, we can call that f dashed of y. In the same way, if we differentiate a function of x with respect to x, that would be f dashed of x. And then dy by dx, we just leave it as it is, So we just stick and multiply, if you like, the dy by dx at the end of the expression for f dashed of y. So, for example, what this would mean is, if you want to differentiate a function of y which was, for example, let's call it y squared by dx, we differentiate that with respect to y. To differentiate y squared would be 2y, then dy by dx. Whereas if we were differentiating a function of x normally, for example, differentiate x squared, that would just give us 2x. So if you differentiate a function of y with respect to x, it works in exactly the same way, 2y instead of 2x, but you just shove a dy by dx on the end of it. That's a quick take-home point to make. So to summarise that point, all we need to do when differentiating a function of y with respect to x, we differentiate with respect to y first, then multiply at the end by dy by dx. We can take this slightly further as well. What if we have a mixture of functions of y and functions of x? Let's now think about the product rule for differentiation. So by the product rule for differentiation, if you differentiate a product, for example, this might be called u, this might be v, uv dashed, we differentiate the first function, if this first function is in terms of x, that's f of x all dashed, leave the second function alone, and then we add on, keep the first function as it is, then multiply by the derivative of the second function. Using what we've just done above, if we substitute in the f of x dashed is just simply f dashed of x, and f of y all dashed is f dash y dy by dx, which we worked out above, we have this here. Now that looks much more horrible than what it needs to be. When we practice it, you'll see that this actually works much nicer than what it appears to look like in this form. But if you like to know your equations and your formulas, I've included it here, so you might want to make a note of that in the margin, or maybe just highlight it or ring it on your notes. Okay, so does it work? Well, the next thing I want to do here is to actually show you that it does work. And so we're going to show the consistency of implicit differentiation with explicit, which in terms of what you think, it just means normal standard year 12 differentiation. So this here, I must stress, do not actually differentiate implicitly with these ones. This is just to show you only that it does work. It's not some sort of magical hack that I've made up to trick you. So these two examples here are just purely illustrative for understanding only. So anyway, we've got y cubed is 8x to the power 9. So we're going to differentiate this in two ways. So part A, we're going to do it the standard easy way, make y the subject and then differentiate explicitly. So we've got here y cubed equals 8x to the power 9. So if I cube root both sides, cube root of y cubed is obviously going to be just y. So we get that y equals, the cube root of 8 is obviously 2. If I cube root x to the 9, that gives me x cubed. So therefore, then differentiate that, we get dy by dx. The 3 comes to the front, times is by the 2, so 2 times 3 is 6, x, then 1 less than 3 goes to 2, so dy by dx of this one is 6x squared. What we could have done, which I'm not suggesting we do, differentiate implicitly works like this. So we differentiate both sides. So imagine this was differentiating x cubed would go to 3x squared. Because it's y cubed, that goes to 3y squared. But like I said earlier, when differentiating a function of y, it works the same way as if differentiating a function of x, but you just shove a dy by dx on the end of it. So we have 3y squared times dy by dx. Then if I differentiate the right hand side, the 9 comes to the front, multiplies the 8, gives 72. 1 less than 9 becomes 8. Then divide both sides by 3y squared. We get that dy by dx equals 72 x to the power 8 all over 3y squared. Now we could leave it like that if a question said leave it in terms of x and y. But just to show you it's the same as what we have over here, y is actually 2x cubed. So if I make that substitution, got 72x to the 8 divided by 3, 2x cubed, all squared, because that is what y actually is. So let's simplify this now. So 72 divided by 3, well, that I'll leave it alone. Well, actually, I'll leave it alone for now. So 72x to the 8. 2 squared is 4, times by 3 is 12. X cubed times itself, x cubed times x cubed is x to the power 6. 72 divided by 12 is 6. X to the 8 divided by x to the 6 is x squared. So we see it does hold up, it does make sense, it is consistent with what we knew all along. So that's dy by dx. We see it's 6x squared again. Let's do a slightly more complicated example. Works example 2. This time we've got x squared y to the power 1/3 equals 5. In the same way, we're going to find dy by dx by first of all making y the subject, then differentiating explicitly, and part B, we're going to differentiate implicitly and show that it works. So part A, let's start with x squared y to the power 1/3 equals 5. So if I now divide both sides, I made a mess of that. Sorry, my 3 looks a bit wonky. There we go. So if I divide both sides by x squared and get y to the power 1/3 is 5 divided by x squared. Then finally, if I cube both sides, y to the power 1/3 cubed gives us y. Then cube the right hand side as well, so cube of 5 gives 125. And x squared to the power 3 gives x to the 6. And if I want to, I can call that 125 x to the power minus 6. So therefore, differentiating that, dy by dx, bring the minus 6 to the front, and multiply it by the 125, so that gives minus 750. The power reduced by 1, so minus 6 goes to minus 7. So I got minus 750 x to the power minus 7. So differentiating implicitly. So what we need to do here is differentiate both sides with respect to x and then rearrange. And so first of all, using the product rule, so differentiate x squared first. I get 2x, leave y to 1/3 alone. And then x squared, leave that as it is, and differentiate y to the 1/3. So the 1/3 comes to the front, reduce the power by 1, so 1/3 minus 1 is minus 2/3. Then because this is a function of y, like I said before, we stick a dy by dx on the end of it. So then we've got dy by dx. Differentiate the right hand side, 5 is a constant, so differentiate that, it gives us 0. What we've got here is different powers of y's, which makes it quite awkward. So what would be quite handy is if we had whole powers of y. So what could I multiply y to the 1/3 by to give us a whole y? Well, I could multiply by y to the 2/3. 1/3 plus 2/3 gives us a full y. So I need to multiply both sides by y to the 2/3. So this bit here will become 2x to a full y. This bit, I've got 1/3 there, so now I'll have plus 1/3 x squared. Y to the minus 2/3 times y to the 2/3, that'll give us y to the 0, which is just 1. So this now eliminates the y to the minus 2/3. Essentially, it's like it's cancelled it out. I still have the dy by dx though, so then I put dy by dx equals 0, like so. So then what we can do is we can then multiply through by 3 is what I'm thinking. So we have 6xy plus x squared dy by dx equals 0. and therefore rearranging, we get dy by dx equals minus 6xy, all divided by x squared. But of course, if we want it to be the same as this, we need to think about what is y. So y, we actually had here, y was 125 over x to the power 6, which is the same as this thing here. And so if I make that substitution, so dy by dx minus 6x times 125 x to the minus 6, all divided by, of course, x squared, running out of space here again. So I'm just saying that y is this thing here. And then hopefully you can see, if you were to simplify this, minus 6 times 125 gives minus 750. X to the 1 times x to the minus 6 gives x to the minus 5. Then divide by x squared gives x to the minus 7. So again, we have exactly the same thing. So we've got here that dy by dx equals minus 750 x to the power minus 7. So exactly the same, which is what we wanted to show all along anyway. Let's now apply our newly acquired skill with some worked examples which are exam style. So, how to differentiate functions implicitly and actually get some marks on these. So, let's find an expression for dy by dx in terms of x and y, it says, for the equation y squared equals sine y minus x squared. So all we need to do here is differentiate the left, then differentiate the right. So if this was differentiating x squared, it would simply be 2x. If differentiating y squared, it becomes 2y. But because it's a function of y, we stick the dy by dx on the end of it. That's the key thing to remember. It works the same as if you're differentiating a function of x, but just shove a dy by dx on the end. This bit here, sine y, this bit is a function of y. If you differentiated sine of x, that would go to cos of x. To differentiate sine y, that'll go to cos of y. But because this is a function of y, again, yeah, you know it now. Remember to put on the dy by dx at the end. Now, x squared, that's just a function of x. So differentiate x squared, that gives us 2x. So now let's get these dy by dx's together on the same side of this equation. So what I'm going to suggest we do here would be to simply get the 2x onto the left-hand side. So if I add 2x to both sides, I'll just make a note of that so you can follow me through. Add 2x there, add 2x over here. I'm going to get 2x plus 2y dy by dx. Over here, I'm going to have cos y dy by dx. Now I can isolate the dy by dx terms by getting them all onto the same side. So if I subtract 2y dy by dx from both sides, I'll then have that 2x equals cos y dy by dx minus 2y dy by dx. Now this bit here, I'm hoping you can see this will actually factorize out. So if I look at the right hand side and factorize out a dy by dx, then I've got cos y and minus 2y. And that equals on the other side 2x. The question says it can be left in terms of x and y, so no need to get it all in terms of x or all in terms of y. To get dy by dx on its own, we can just divide through by this whole bracket. So therefore, dy by dx simply equals 2x, all divided by cosine of y minus 2y. Let's do another example. This time, find dy by dx, again in terms of x and y, for this expression here. So same idea, differentiate the left, differentiate the right hand side. So on the left hand side, 3x squared, that'll differentiate to 6x. If this were minus x, that'll differentiate to minus 1. Because it's minus y, that'll differentiate to minus 1 times by dy by dx. So 1 times dy by dx is just dy by dx. X differentiates to 1. X to the 4 will differentiate to 4x cubed. Y to the 4 will differentiate to 4y cubed. That's a minus, of course. And then, of course, because it's a function of y, you get the idea now, I'm hoping, stick dy by dx on the end. Differentiate the right hand side, 2 is a constant term, so this differentiates to 0. Next, I'm going to factorise out the dy by dx on this side. So I have dy by dx, so I've got 4y cubed here, minus 4y cubed rather. This is minus dy by dx, so again minus 1. And then I've still got a plus 6x and a plus 1, which equals 0. Rearrange slightly. I've got dy by dx minus 4y cubed minus 1. If I now subtract the 6x and subtract 1 from both sides, I'll get minus 6x minus 1. Therefore, final step, I can work out what dy by dx is by dividing through by this bracket. So dy by dx equals minus 6x minus 1, all divided by minus 4y cubed minus 1. Now that's absolutely fine as an answer, completely correct. However, if all those negatives don't sit well with you, what you can do is write it in a different form. If you want to, completely optional. If I were to multiply both sides of this fraction by minus 1 to keep it equivalent, that's the same as saying it's positive 6x, positive 1, all over 4y cubed plus 1. So that's the equivalent fraction to that one. This one looks a bit better. Either or is absolutely fine. Question 3. I've got a curve, C, defined implicitly in terms of x and y as e to the 2x ln y equals x plus y minus 2. Use calculus to show that the equation of a tangent to the curve C of a point 1, 1 is y equals 1 over e squared minus 1x plus e squared minus 2 over e squared minus 1. Now, as horrible as this sounds, let's just think about it step by step. We're wanting an equation of a tangent. A tangent is a straight line, okay? So a tangent is a straight line, so it's going to be of the form y equals mx plus c. So what we can do here, we need to show that the gradient of this tangent must therefore be this, and the y-axis intercept we need to show must be that. That's hidden within this question. To see that straight away will help the understanding. What we need to do, because it says to use calculus, you need to differentiate both sides implicitly. So e to the 2x, use a product rule on this bit. So differentiate e to the 2x, leave ln y on its own. E to the 2x differentiates to 2e to the 2x, leave ln y as is. Then using the product rule, hold e to the 2x constant, differentiate ln y. Ln x will differentiate to 1 over x, so ln y differentiates to 1 over y. Because it's a function of y, we tag on dy by dx at the end. On this side, differentiate x gives us 1, differentiate y will give us 1 times dy by dx. Differentiate minus 2, that minus 2 will vanish. So what we can do now is actually substitute in the point 1, 1. So now, if I sub x is 1 and y is 1, as per the point we're given, then we can actually work out what the gradient is, dy by dx, at that point. So 2e 2x means 2 times 1, which is 2. ln y will be ln of 1. plus e squared times 1 over 1 dy by dx equals just 1 plus dy by dx. So ln1 is 0, so this vanishes, that becomes 0. So I've got 0 e squared dy by dx equals 1 plus dy by dx. I can then isolate and get all the dy by dx's onto the same side of this equation. So what I can do here, if I take away dy by dx from both sides, I then get e squared dy by dx minus dy by dx equals 1. I can then factorize out the dy by dx, so get dy by dx brackets e squared minus 1 equals 1. So therefore, at the point 1, 1, dy by dx equals 1 over e squared minus 1. So that here is the gradient of the tangent to the curve at the point. So I worked out m is, whoops, wrong colour, is 1 over e squared minus 1, which if I scroll up now, that's what I wanted to prove, so I've got part of it. Now all I need is to find the y-axis intercept. So that's our next step to this problem. So we can now say about the equation of the tangent at 1, 1. So therefore, tangent at 1, 1 is going to have the form y equals mx, which is 1 over e squared minus 1x plus c. So to find out what c is, we can simply again substitute in a point we know. So again, if we sub in x is 1 and y is 1, we can work out what c must be, because we know it needs to go through when y is 1. So sub x is 1 and y is 1 into this again, we can then work out what c needs to be. So 1 equals 1 over e squared minus 1 times 1, which can just leave us just as it is, plus c. So then c must be 1 minus 1 over e squared minus 1. So if I rewrite 1 as e squared minus 1 over itself, minus 1 over e squared minus 1, I can then combine this into a single fraction because you've got a common denominator. So e squared minus 1 minus another 1 gives e squared minus 2 over e squared minus 1. So that's what c is. So c is e squared minus 2 over e squared minus 1, which, lo and behold, that's what I wanted to show all along. So I've actually got it. So we worked out the gradient of a tangent, we worked out the y-axis intercept of a tangent, therefore we've got the full equation of the tangent of a point 1, 1. So therefore conclude equation of tangent at the point 1, 1 is therefore y equals 1 over e squared minus 1x plus e squared minus 2 all over e squared minus 1. Then we're done. So it's now over to you to try some of these questions on your own. So, suggested questions. Exercise 9H in the book, page 255 to 256. Try question 3, then go straight on to the exam style questions to give you a good grounding on the skills needed. So try these, see how you go. You know what to do if you get stuck. Please ask for help either online in the comment section or come and see me in class. I don't mind as long as you do ask to not suffer in silence. Thank you very much for listening and watching, and I hope to see you all again very soon. So take care and goodbye from me.